It's almost here. Since thou hast called upon...
difference between this probe and this clip at a rate of 2 billion times per second. This is the instrument that's literally collecting and saving the data for this camera. Imagine we have some time-varying signal passing into the scope on these wires. Every half a nanosecond, the oscilloscope looks at the signal, measures it, and records the number digitally in RAM. It's doing this all the time, continuously saving data. But if it receives a specific signal, like a particularly strong or a particularly sharp signal, then it stops recording, takes the saved data, and plots it to the screen as a value of voltage over time, or in our case, with data from this sensor, light intensity over time. One really wacky thing I want to point out.
Okay, so you're probably going to expect me to have notes on his video, and I don't. Actually, there's very little notes that I have on this. It's just freaking awesome. Except for, it totally destroys, besides the fact that it totally destroys the twin paradox, because of the whole idea of perspective, is that, like, this whole thing right here.
The same path, so it kind of doesn't matter. This is not true, however, for information traveling outside the camera.
Right.
This camera can perceive the motion of light because light traveling this path gets to the camera faster than light traveling this path. In the first case, light may take 5 nanoseconds to get to a droplet of fog in the air, and then maybe 15 nanoseconds to bounce all the way over to the camera. And in the second case, maybe 15 nanoseconds before it has hit some fog, then 15 nanoseconds to get to the camera. This extra path length is what the camera perceives as a delay. And it only works perfectly because the path back to the camera is the same length in both cases. The camera is seeing the light at this location and the light at this location both 15 nanoseconds in the past. If you look at this video and think, wow, the light at the beginning seems to be a tiny bit faster, then you are really observant. It's slight. But with this camera, the path light takes to get to the camera is critically important.
Like, that, just measuring, because light is so fast, even distances inside of a garage is enough to skew the distance and therefore the time it takes to record a motion of light. You don't need more than that, which is so freaking cool.
When we point the camera in different directions, what we're really probing is this set of path lengths.
Yeah.
And this distance to the camera is not the same as this distance to the camera, so things get weird. When we reposition the camera to be behind the laser, this effect is much more extreme. As the light reflects from farther and farther locations, it not only takes light longer to get to the place where it scatters, but it takes longer to get back to the camera.
The same effect was stated in the famous TED Talk Twin Paradox video, which is just radical how they fail to see this general thing. It just takes longer for the light to be perceived. It doesn't mean there's some time variance on it. It's all happening normally. There's no space-time curvature nonsense happening in the garage. So we have to conclude that any time variance stuff is just something simple.
Camera. Because we're basically doubling the path length for the light, the speed of light appears to be almost half of its true value. If you want to think about this another way, from some sort of classical objective perspective, the camera sees things near it with very little delay, but sees distant objects farther and farther back in time. The image formed by this camera...
Well, that's just rational perspective, honey. That's just rational perspective. You don't need to be simple classical. By the way, light is simple classical, but never mind. And time is linear? Said someone.
Is not an objective view of the world at a single moment in time, but a perspective taking a slice obliquely through time. For the
Yeah.
light bouncing back towards the camera, or equivalently, if we put the camera at the far end of the garage, we have the opposite effect. If we look at the path lengths for each position in this case, the total path lengths are almost the same. As the scattering location gets farther from the light source, it also gets closer to the camera. So we really can't detect much of a difference in travel time. With both mirrors set up so the light can bounce back and forth many times, we get to see both the artificial slowdown effect and the artificial speed up effect in the same clip, and it looks pretty trippy.
Yeah, and that's just an artifact of how it takes longer for light from a distance to get to us than light that's closer, and it's amazing that that can even happen at these scopes. But you have to understand, why would it take any further distance in order to prove this? It just is different, and just seeing it in real time at this speed can prove like a very simple thing about how light being perceived. The comparison to the twin paradox is really hard to convey, but for whatever reason, they had this idea that signals being sent from some ship going at 86% the speed of light would be perceived as somehow happening at... And here's the thing, my kind of perspective, I don't have the ability to convey whatever it is that they were trying to say about it without putting on my own narrative. In other words, everything is in my perspective. I don't have their story in my head as something I care to even mention. But, if you must...